Hello, good morning, good afternoon, good evening. This is Lecture 1 of ComSci 141, Introduction to Automata. Before we start, I would like to give a small disclaimer. I'll be doing this recording in one take, so I won't be pausing or editing the video. And if you hear me cough or stutter or pause in the middle, please excuse me for doing so. Okay, so let's start. For today's topics, we'll discuss automata and the basic concepts like strings, alphabets, and languages. So what is automata theory? Automata theory studies automata or automaton for singular, which are abstract computing devices. So when we say abstract, it means that they don't actually exist in the real world. It's only in the mind, right? Or yeah, abstract. Automata theory is closely related to formal language theory. That is why our ComSci 141 is entitled Automata and Language Theory. And later on, we will see that a certain automata has a corresponding language associated to it. So automata are theoretical machines. And what this does is it abstracts the attention away from any particular kind of computer or programming language. So it doesn't matter if you're using a PC or a laptop or a MacBook, or if you're using Windows or uh, Mac OS, or if you're using Python or C, because it's only a theoretical machine, right? So it's designed to be examined mathematically, not an actual computer. So the mathematical models strip the computational machinery down to the bare minimum. So we try to remove all the unnecessary parts of a computer if we are only to focus on the computing part. So it's not really used for practical programming problems. So if they're not used for practical programming problems, why do we need to study them? Number one, mathematical models are equivalent to real computers and real programming languages in terms of computing power. So any problem that's solvable on a real computer can be solved using these models and vice versa. That's in theory, right? So we can strip away all the unnecessary details to make a mathematical model, and the capabilities of the mathematical model are just the same with a real computer. Okay? Now, why do we need to study automata? So we have three reasons. Number one is for finite automata. Number two, for structural representations. And number three is for complexity. And of course, it's also related to other computer science fields, like the theory of computation, compiler design, parsing, artificial intelligence, and natural language processing. These are some of the branches of computer science where automata is also related to. Now, let's go through each reason why we need to study automata, starting with finite automata. So finite automata is just a finite state machine. So finite means it's countable, it's not infinite, right? So it has a finite number of states. For example, a light switch. So a light switch has an on state and an off state. So there are two states. So the advantages of having finite states is that you could implement a system with a fixed set of resources. Since you could count the number of states, then you could have a fixed number of resources as well. It's useful. It is a useful model for many important kinds of hardware and software. So in a finite automata, state remembers only the relevant portion of the system's history. It doesn't need to remember the entire history, only what's important. So for example, for a light switch, doesn't need to remember how many times you have already clicked, right? So it only needs to remember what the current state is, which is either on or off. Okay, so it doesn't need to remember anything else. So some applications of finite automata include verifying systems with finite and distinct states. For example, communication protocols. So if you have all the possible states, like is the message sending successful or failed or lost, you could test all of those because you have a finite number of states. You can also design and check behavior of digital circuits. You can also use it for a lexical analyzer of compilers. So this is the part that breaks the code or the text into tokens. And we also use this for word or phrase or pattern searching in text using regular expressions. Okay, so those are applications of your finite automata. Next, we study finite automata because of structural representations. Example of which is grammars. So grammars, which look like this, are useful models for software that process data with recursive structure. So later on in the second part of the course, we'll be looking at context-free grammars, and these are used in parsers. So the parser is the component of the compiler that deals with the programming language syntax. So this is the part that tells us there is a syntax error if it doesn't follow the correct syntax. Okay, so we use a grammar to define the syntax. Another structural representation is regular expressions. So you've probably seen regular expressions before. So it looks something like this. So this one matches a password, right? So regular expressions are used in pattern matching and also in form data validation. Like, is it a valid email? Is it a valid password or valid username? Okay, so pattern matching. Okay, so those are structural representations. And finally, the third reason is study complexity, which is studying the limits of computation. So we have two branches, which is decidability and intractability. Decidability asks, what can a computer do at all? So divides problems that are solvable by computers versus those problems that are not solvable. Okay, so what can a computer solve and not solve? So that's decidability. The other branch is intractability. So this divides problems that are solvable by a computer in reasonable time versus problems that are solvable in theory, but it takes too much time in practice. Okay, so we assume that the problem is solvable in theory, but what problems can be solved in reasonable amount of time or quickly versus those that are it will take too long, right? So solvable siya, but it will take years siguro to solve. So that's the tractable versus intractable problems. So we'll learn about this more in the third part of our course. So those are the three reasons why we study automata. So finite automata, structural representation, and complexity, which actually maps directly to the three topic groups of ComSci 141. Okay, now let's talk a little bit about the history of automata. So the first guy who really studied automata was Alan Turing. In 1930s BC, or before computers, Alan Turing studied an abstract machine that had all the capabilities of today's computers in terms of what they can compute. His goal studying this machine was to describe the boundary of what a computing machine could and could not do. And this machine was called Turing machines. Okay. Next, we have McCulloch and Pitts. In the 1940s, Warren McCulloch and Walter Pitts invented finite automata. They originally proposed to model the brain function for neural networks. Next, We have Noam Chomsky, who was a linguist. In the 1950s, he studied formal grammars. Although this is not a finite state machine, but formal grammars are closely related to abstract automata. Next, we have Stephen Kleene, 1950s. Stephen Kleene invented regular expressions. He also showed the equivalence of the finite automata and regular expressions, which we will also study in a later part of the course. Then, in 1969, Stephen Cook extended Turing's study of what could and could not be computed. He studied the intractability problem. Now, what if in 2020, student with the student number something something takes ComSci 141 and makes a breakthrough discovery in automata theory? Who knows, right? So, yeah, hopefully that happens. Anyway, that's the history, the brief history of automata. Let's now go through the central concepts of automata theory. So we'll talk about alphabets, strings, and languages. Let's start with alphabet. So you already know about English alphabet or alphabets from your kindergarten days, probably. But in automata theory, we call the alphabet is a finite, non-empty set of symbols. So finite, it means that it's countable, and it's non-empty, so there's at least one symbol. Usually denote an alphabet by sigma. So as an example, we have sigma is equal to 0, 1. So that's the binary alphabet. So you only have the symbols 0 and 1 in your alphabet. Next, you can also have the alphabet with the set of all lowercase English letters. That's from A to Z with all lowercase. And you also have the set of all ASCII characters. There's a lot of different possible alphabets. Okay. Next, strings. String is a finite sequence of symbols chosen from some alphabet. It's also known as a word. So alphabets are a collection of symbols. A string is a concatenation of different symbols from an alphabet. Note that this is different from your programming language strings, the one with quotes. Okay, so our strings in automata doesn't need to have quotes. For example, 01101 and 111 are strings. So take both strings from the binary alphabet, which contains 0 and 1 as the symbol. Okay. Now, there's something called the empty string. So it's a string with 0 occurrences of symbols. So it's empty. And this is usually denoted by epsilon. So when you see epsilon, that means that it's the empty string. And you could choose the empty string from any alphabet because there is nothing to, there's no symbol to choose, basically. Take note that space is not empty string, okay? Space is one character, it's the space character, and they're not the same with the empty string. Next, strings have length, right? So the string length refers to the number of positions for symbols in the string. So the length of string W is usually denoted by two bars, two vertical bars. So length of W. For example, the length of 011 is 3 because there are three symbols. The length of the empty string is 0. And the length of the space is 1 because again, even if we can't see it, there is actually one space character in there. Okay? Now, you might wonder why we call string length or we define string length as the number of positions for symbols. Why don't we just say the number of symbols in a string, right? So number of symbols is colloquially accepted, but it's not entirely correct. Why is that? So, for example, in the string 01101, so there's supposed to be 5 symbols, right? So the number of symbols are actually only 2, because there's only symbol 0 and symbol 1. So if you say the number of symbols is 5, that's wrong, because there are only 2 symbols. There are 5 positions for symbols, that's why string length is 5. Okay, so that's just a technicality, but generally when we say number of symbols, we generally mean the number of positions. Okay, so yeah, that's string length. Next, let's talk about alphabet powers. Now, the set of all strings of a certain length from the alphabet sigma can be expressed using exponential notation. And this is what we call the alphabet power. For example, sigma raised to k is the set of strings of length k, each of whose symbols are part of the alphabet sigma. So what does that mean? For example, sigma raised to 0 means that you take all strings that you can form from the alphabet sigma with the length 0. But there's only one string with length 0, which is empty string. So it's empty for any alphabet sigma. Okay? Uh, Epsilon is the only string with length 0. Okay, let's see more concrete examples. So let's say that our alphabet is the binary alphabet, or 0 and 1. So sigma raised to 1 is equal to the string 0 and string 1. If it's sigma raised to 2, it means that we need to make all of the length 2 strings from the alphabet sigma. So that would be 0, 0, 0, 1, 1, 0, and 1, 1. Okay? How about if it's sigma 3? If it's sigma 3, then there would be 8, right? 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, and so on. So there should be a total of 8. Okay? Now, there could be some confusion between symbols and strings. If it's only the alphabet that you are referring to, that would be individual symbols. But if it's, let's say, sigma raised to 1, that means that you're actually making strings of length 1. So sigma raised to 1, those are strings. If sigma lang, that's symbols lang. Okay? So please don't be confused by that one. Now, there's also a special alphabet power called sigma star, and this is the set of all strings over the alphabet sigma. So all possible strings, whatever the length is. So star means that it's a wild card. So whatever the length is, it's part of it. So sigma star is actually sigma 0, union sigma 1, union sigma 2, union, and so on. So all possible lengths. Okay? So for example, for if your sigma is 0, 1, if you take the star of that one, sigma star, then you get all possible binary strings. So starting from epsilon, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, and so on. Okay? So set of all strings over the alphabet sigma. Now, there's also sigma plus, which is similar to sigma star, but it's the set of non-empty strings from the alphabet sigma. So everything in sigma star except for epsilon, basically. So sigma plus is just starting from sigma 1, union sigma 2, union sigma 3, and so on. Okay? And sigma star is sigma plus union epsilon. So you just add the epsilon to have the sigma star. Okay? Next, let's talk about concatenation. So given two strings x and y, xy denotes the concatenation of x and y. So meaning you put the two side by side with each other. So for example, if x is from a sub 1 up to a sub x, and y is from b sub 1 to b sub y, xy would just have the concatenation b1 to ax, b1 to by. Okay? The length of your concatenated string xy is just equal to the sum of the length of x and the length of y. So pretty straightforward. So example, if x is 0, 0 and y is 1, 1, xy would be 0, 0, 1, 1 and yx would be 1, 1, 0, 0. Okay? Now, for any string w, if you concatenate the empty string to it, so for example, epsilon w or w epsilon, it's still going to be w. So epsilon, or the empty string, is the identity for concatenation, similar to how 0 is the identity for addition. So even if you add the empty string to another string, it will still be the original string. Okay? So that's it for strings. And finally, we have languages. So a language is just a set of strings. All strings are chosen from some sigma star, where sigma is a particular alphabet. So if a language L is a subset of sigma star, then we say L is a language over alphabet sigma. Language over sigma need not include strings with all symbols of sigma. So if I say that uh, my language is over the alphabet containing lowercase English letters, the strings in my language doesn't have to include all the symbols, but all strings has to get their symbols from the alphabet. Does that make sense? And then, if L is a language over sigma, L is also a language over any alphabet that is a superset of sigma. So let's see an example. Let's say that your language contains 4 strings. You have 0, 0, 0, 1, 1, 0, and 1, 1. So we say that this language is a language over the binary alphabet, right? Because we take all the symbols from the alphabet 0 and 1. But this is also a language over the alphabet containing the digits 0 up to 9. Because even if we did not use 2, 3, 4, 5, 6, 7, 8, 9, the language that we have containing the 4 strings still derived its symbols from this bigger alphabet. Okay? So that is what we mean by this statement here, that if L is a language over sigma, L is also a language over any alphabet that is a superset of sigma. So the second alphabet here, 0 to 9, is a superset of the binary alphabet, which is also only 0 to 1. Okay? Yeah. Now, next, sigma star is a language for any alphabet sigma. So sigma star is a language by itself. And we also have null, which is called the empty language, and it's a language over any alphabet as well. So the empty language is a language that doesn't contain any strings. There's also another language which only contains the empty string. It's also a language over any alphabet because, well, you can get the empty string from any alphabet because there's nothing to get, right? Take note, however, that the null or the empty language is not equal to the language containing the empty string, because null or empty language has no strings at all, but the language containing the empty string has one string, which is empty. Okay, so don't be confused by that. Now, languages can have infinite number of strings. So most languages that are defined through sigma star have an infinite number of strings. However, they are restricted to consist of strings drawn from one fixed finite alphabet. So even if a language could have multiple infinite strings, the set of symbols that it draws its strings from is fixed. Okay? So finite ang alphabet always. You can't have an infinite alphabet because then uh, there is no bounds to what you can create. Let's see examples of languages. So a language of all strings consisting of n zeros followed by n ones for some n greater than or equal to 0. So you have, let's say, some number of zeros followed by the same number of ones, but it could also be empty because n could be equal to 0. So this language consists of the empty string because, well, if n is 0, then it's empty. Then you have 0, 1, to equal number of zeros and ones. Then you have 0, 0, 1, 1. Then 0, 0, 0, 1, 1, 1. Okay, so n zeros followed by n ones for some n greater than or equal to 0. Next, we also have the set of strings of zeros and ones with an equal number of each. Now, how is this different from the previous example? In the previous example, we said that all the zeros has to be contiguous at the start, right? They have to be successive and then followed by contiguous ones as well. But here, there is no such restriction. The only restriction is that we only need to have an equal number of zeros and ones. So the language will consist of strings epsilon, empty string because there's an equal number of zeros and ones, which is 0. You also have 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 0. So everything that has an equal number of zeros and ones, it's part of this language. Then we also have the set of binary numbers whose value is prime. So your prime numbers include your 1. So 1, no, 1 is not prime, but 2. 2 is a prime number, and then 3, and then 5, and then 7, and then 11, and so on. Okay. Uh, Now, when describing a language, we usually also use something called the set former notation or set builder notation, which you've probably also seen in your earlier math classes. No? So it's commonly used to describe a language. So syntax of the set former notation is you have the curly braces, and then you have something about W, that's the string, then vertical bar, and then you write something about W after that. So, for example, W, where W has an equal number of zeros and ones. So, or string W, wherein W is a binary integer that is prime. So you can write it that way. Okay, you can be descriptive. The set former notation is also uh, it's also common to replace W by some expression with parameters and describe the strings in the language by stating the conditions on the parameters. So instead of just writing string W, we could express the string better with some variables. For example, instead of writing string W, you could write 0 raised to n, 1 raised to n. That means that there are n zeros followed by n ones, wherein n is greater than or equal to 1. Okay, so this was the um, first example that we had earlier. Language of all strings consisting of n zeros followed by n ones for some n greater than or equal to 1. Okay. Next, we also have 0 raised to I, 1 raised to j, wherein I is greater than or equal to 0 and j is greater than or equal to I. So it's I is between 0 and j. So what this means is that the language consists of strings with some number of zeros, but it's possibly none because 0 raised to I and I could be equal to 0. So there could be no zeros at all. So some strings with some zeros followed by at least as many ones. So that means that if you have two zeros already, the number of ones could be 2 or more. So pwedeng nga 2, 3, 4, and so on. Because j, which is the number of ones, should be greater than or equal to I, which is the number of zeros. Okay? Now, lastly, there is something called the membership problem. So if L is a language over sigma, given a string W which is part of sigma star, decide whether or not the string W is part of the language. So we call this the membership problem, and we'll revisit this one later on when we discuss finite automata. Okay, so as an example, let's go back to the previous language that we have, the 0i 1j, wherein 0 is less than or equal to I, and I is less than or equal to j. So given this language wherein you have some number of zeros followed by at least as many ones, are the following strings in L: 0, 0, 1, 1. So this string is part of the language because you have at least as many ones as zeros. Next, 0, 0, 1, 1, 1. Yes, this is also part of the language because there are more ones than zeros. How about this one? 0. No, it's not part of the language because there should be at least as many ones. So there should have been at least one, one. Isa ka one. Okay? Should be at least isa ka one in this one. Okay. How about this one? 0, 0, 1. Is this part of the language? No, because there are already two zeros and you only have isa ka one, 1, 1, right? So um, it's not part of the language because the number of ones has to be at least as many as the zeros. How about 1? Yes. In this string, you have no zeros, but you have 1, 1. So the number of 1 exceeds the number of zeros, so this is valid. Okay, so that's it. So to review, we discussed about the alphabet, which is a finite, non-empty set of symbols. Okay, so it should be finite. There must be a limit. Then you have the string, which is a finite sequence of symbols. It can be an infinite string as well. And then you also have the empty string. And then the language is a set of strings. Okay, so that's the basics of your automata theory. For our next topic, we will discuss finite automata, and we'll start with the first type, which is deterministic finite automata, or the DFA. So these are the references, and so that's it for today, and I will see you next time.